Hi everyone. So my name is Caprice Phillips and my pronouns are she, her, and hers. I'm a PhD student at The Ohio State University working with Dr. G. Wong, and today I'm going to be talking about the research that I've been working on involving detecting potential biosignatures in the atmospheres of gas dwarfs with the James Webb Space Telescope. Before I get started, I wanted to introduce my collaborators. My advisor is Dr. G. Wong here at OSU. Then we also have Sarah Kendry at the Space Telescope Science Institute, who's an expert with MIRI. We also have Tom Green, who works at NASA Ames, who's a near-spec expert in Ren Yu. At JPL, who does photochemical modeling, and Joe Schultz and Wendy Pinero, who are both in the geology department and helpful with interior modeling, and then Jeff Valenti at the Space Science Telescope Institute was also a NewSpec instrument. So we've assembled a really great team of experts with different instruments with aboard JWST. It's been really great working with all of them. So gas dwarfs are among the most abundant type of planet. So this is the type of planet that my research focuses on. And so in 2014, Buchave et al. Worked on a paper where they broke exoplanets up into three categories based on solar metallicity, and there were those below 1.7 Earth radii and above 3.4 Earth radii, but the ones in between were dubbed gas dwarfs, which they said were planets with rocky cores and hydrogen helium envelopes, and those include both super Earths and mini Neptunes. And so this is a diagram shown here. It's a little outdated, but it's the number of planets versus the type of planets here, and highlight are super Earths and sub Neptunes, showing that they're the most common type of transiting planet by size, which is what my research focuses on. So what's interesting about these types of planets is that they are not found in the solar system. We have a very structured solar system where we have the inner rocky planets like Mercury, Venus, Earth, and Mars. We have gas giants like Jupiter and Saturn, and then we also have ice giants, Uranus and Neptune. And so gas dwarfs are not found in the solar system. So it begs the question, are they upscaled versions of the inner rocky planets? Are they downscaled versions of the gas giants, for example? And it brings forth questions about like their formation and information about like the atmosphere, and if their biosignatures or potential signs of life are different in these types of planets, which is what I focus on. So ammonia as a biosignature. So this was first proposed by Sarah Seeger in 2013. And so the idea is that ammonia as a biosignature in an atmosphere rich in hydrogen and nitrogen, the idea is that you might have microbial life that can break apart the bonds to produce ammonia, and eventually have an access to build up in the atmospheres are hopefully detectable levels, and these microbial lives can capture the energy release, and the excess of ammonia, like I said, will build up in the atmosphere to potentially detectable levels. And ammonia is a really cool biosignature in the potential biosignature in the fact that you need really high temperatures and pressures to produce it abiotically. So that's kind of the idea. If you were to see potentially detect ammonia in the atmosphere, it could be the first steps to start to rule out abiotic processes and different things like that. So my research focuses on if we can detect ammonia in the atmospheres of these gas dwarfs. So before we can even see whether we can detect ammonia, we first have to select targets. And so we've used three main selection criteria, and the first one, we ask like kind of three questions, like can the planet support liquid water, does the planet have the right pressure, and third, is the planet close enough to Earth. And so we want it to have the right pressure between 1.7 and 3.4 Earth radii, and the upper cut is to make sure that it doesn't have too high of a pressure to produce ammonia abiotically do the habit process like here on Earth. And so we want to make sure that the planet has the right temperature, support liquid water, make sure it's not too hot, and then also we want to make sure it's close enough so that we have adequate flux from the whole star and the planet. So based on this selection criteria, we have a sample of 7 targets shown on the right here. This is the plot of the planet radius versus the equilibrium temperature of our 7 targets. We have targets like K218b, LHS 1140b, a couple of planets in the TOI 270 system. So the targets are shown here in the color, and the ones in the gray dots are the ones that meet the first 2 criteria but are more than 50 parsecs away, for example. So we don't have the spectra for these objects yet. So what we have to do is have to simulate, we have to simulate the spectra. And so what we do that using this code called Petite Red Trends, developed by Paul Moliere in 2019. So it's a really cool program, and that what you do is that you can insert an abundance of molecules. You can edit the concentration of ammonia and different things like water. You can add Rayleigh scattering, different things like that. And so you can also input pressure temperature profiles. You can edit the surface gravity, the size of the planet, the temperature of the planet, and where you want the pressure bar to be set at. And if you would like to, you can account for the effects of cloud depth as well. And so on the right here is showing the example of the model outputs. And so on the top here is showing some kind of like near infrared, like transmission spectroscopy of an example planet. And on the bottom here is emission spectroscopy showing the mid infrared to see whether we can detect ammonia features as well. But these are the model outputs for Petite Ray Trends. So this slide encompasses basically the structure of this research project. So the first step is to build the, after we've built the spectra, we determine the amount of ammonia in the atmosphere. And we start with a base amount of 4.0 ppm in the atmosphere. And also that's step 1. And so step 2, we select an instrument to test. So there are a lot of ammonia features in the near infrared. There's also a pretty dominant ammonia feature in the mid infrared. And so we utilize different instruments to test whether we can detect these different features. And so for the beginning at the top here, we use the MIRI instrument, which is the mid infrared instrument aboard JWST, which can, there's around a 10 micron ammonia feature that we want to see if we can detect with emission spectroscopy. And so we move on, select the instrument, and then we vary the amount of hydrogen in the atmosphere. And we either choose a 90% hydrogen dominated atmosphere or a 25% hydrogen based atmosphere, which changes the mean molecular weight of the atmosphere respectively. And after that, for MIRI, we want to ask the question if we can determine if the ammonia feature can be detected. We ask if the contrast between the planet and the star is greater than or equal to 10 to the -4, which is a sensitivity threshold for MIRI. And so we kind of go back to step 2 with the near spec instrument, which operates in the in the near infrared. And so we go back and then we vary again the amount of hydrogen in the atmosphere. And so with a 90% based hydrogen atmosphere, we also want to we also want to see the effects that clouds have on the detectability. And so we do clouds versus no clouds here. And then for NIRI with transmission spectroscopy, we ask is the signal to noise for these ammonia features greater than or equal to 3 sigma, determine if that's a detection or not. So we found that transmission spectroscopy is better suited to detect ammonia features than emission spectroscopy. So as I mentioned with transmission spectroscopy, we test a variety of instruments and modes like the near spec and the near res instrument. And this is an example spectra of TOI 270. See here, this is our simulated spectra from Petite in the orange here, and the black dots are the simulated observations from JWST from the respective instruments shown down here at the bottom, and at the bottom panel is a corresponding signal to noise for the different features. So if we take one feature, ammonia feature, for example, the 1.5 ammonia feature here, we see that with transmission spectroscopy, we would get a signal to noise of 5 sigma, which is great, which would mean you would be able to detect this feature using that instrument, for example. However, when we go over to emission spectroscopy, with MIRI, as I mentioned before, there's a ammonia feature around 10 microns, and we see that most of the targets here are below that sensitivity threshold for MIRI, and even our best target, LP79118C, is barely above that sensitivity threshold, so it'll be very difficult to detect this feature there. And so as we did this project, we also wanted to test the effects that varying the amount of hydrogen in the atmosphere has for ammonia detection. And we see that with a 90% hydrogen-based atmosphere for that same 1.5 ammonia feature, we have almost a double signal to noise value. You go from a 5 sigma to a 25% hydrogen-based atmosphere to a 2 sigma detection. So we wanted to explore those effects, and we see that it's better to have a higher concentration of hydrogen in the atmosphere to detect ammonia. Another thing we wanted to explore is the effects of clouds. We see that clouds higher in the atmosphere, cloud decks higher in the atmosphere do kind of mute and flatten the transmission spectra, and so that's another effect that we wanted to see. We tested a variety of cloud decks. With that, I'll just put up my conclusion slides. And so we see that gas dwarfs are more massive and common than Earth, and are promising sites to look for signs of life. And ammonia is an exotic biosignature unique to hydrogen-based atmospheres of gas dwarfs, including super Earths and many Neptunes. And we found that the NIRSPEC instrument is better suited to MIRI to detect ammonia than NIRSPEC and NIRES instrument. And we explored the effects of detectability of ammonia by seeing how it's affected by the concentration in the atmosphere, the amount of ammonia present, and the presence of clouds. So thank you for listening to my talk, and I hope you have a good day.